start the class today. Okay, let me share my screen. Okay, this one. Okay. So this works. Okay, this seems to be working well. Okay.
So by the way, hello.
Yeah, please go ahead. Yeah.
Yeah. Did you decide the course timings as in the Monday or Wednesday thing?
So it looks like Monday is the time that works for most people. So we'll go for Monday. Okay. Okay. So the class schedule will be this as follows. We won't do any further changes. To 5:30 p.m. Friday 2 to 5 p.m. Okay. It might stretch a bit on Fridays. Okay, that's what we have, especially if we have to make up some classes. Okay, for example, next week we will neither have a Monday class because on Monday I'm on leave, and on Friday we will have a departmental symposium. So both the classes are not possible on next week. But the following week, because I did not know about the Monday class, I have accepted I will be giving a talk somewhere on Monday at this time. So which means again I cannot teach the Monday class on the following week, which is 16th. So after today, the most likely next class is the Friday 2 weeks from now. Okay. But I will see if it's possible to do a makeup class sometime in the week of 16th. About now, just so that everybody is clear. So this is an absolutely compulsory. You cannot miss this class, irrespective of whether you're auditing or crediting. Okay. And for crediting students, remember that the Friday classes also carry an assignment submission. So therefore, it will add to a credit over time. And for Monday class, of course, strongly recommended, but only if you have a conflicting schedule, then watch the recorded videos. Okay. Otherwise, again, I expect that you attend. Primarily because this is a slightly more mathematical class. It becomes harder and harder the more you miss the classes. Okay. So again, both are compulsory, but you are exempted from attending Monday class only if you have a conflict. Okay. So that's about that administrative work for today. Let's not spend more time on that. And let's get to doing some interesting work. Okay. So now before we dig into the sort of specific topic that I want to discuss today, I want to discuss some general broad issues. Now, if you all remember in the last semester, our course on basically theoretical ecology, we studied predominantly, one type of problems, right? Okay, there was this focus on how populations change over time, right? Okay. It was the sort of predominant focus of previous semester, and we wrote equations of this. Okay, and we sort of we discussed at length sense of this type of models, what are the various biological contexts where these models make sense and are useful and so on. Okay, so now let us step back a bit. So if you think of biological world, one useful way to think about biological world is in terms of what we call broadly scales. Okay, now the scales come in sort of three dimensions. Okay, so the one obvious dimension is that of time. Another obvious dimension is that of space. And for example, much of the studies that we did in the previous semester was trying to look at over time, how populations are changing, right? And and when we were doing this, we sort of took two approaches. We sort of took in a very fine, sort of what we call. In fact, we took two approaches. One was a continuous time and one was a discrete time approach. I'm going to write it this way. The time was as two possible ways. Continuous or discrete. Okay, and then we sort of entirely ignored this axis of space. Okay, we fully had ignored this axis of space. Okay, and in addition to these two, of course, when we think of this time, we can we can sort of try to think of this time at in many ways. What do we mean by a time in a biological natural times can be, and this generation is of course a time scale that is relevant to a given species. Now you could work at much smaller time scales in generation, and you could see what happened beyond generations. And in fact, much of our focus was on looking at what happened across generations. Okay, I think given that I have written it this way now, I should probably swap the discrete and continuous. So if I were to look at very coarse times, then we end up having discrete generation. But the finer and finer you observe, you have a continuous time scale, right? Now, so much of the population dynamics was looking at really how populations are changing across generations. Okay, irrespective of whether we use a continuous time framework or discrete time framework. However, there is a third important practices which was implicit. We did not think much about it. Not did we think much about the space. Space was entirely ignored in all of our discussions, which is that of what we call hierarchical organization, where we can go, let's say again, somewhere near the origin, we can think of something like individuals, which are basically the fundamental biological units. Okay, and then you have many individuals who form groups, and then groups of these individuals are a large number of the individuals of same species. You will have populations, and then we have many populations, and then you have many populations of many species, and what we call them communities. And then if we sort of keep on going, we will have all the way to ecosystems. Okay. So much of the previous discussions we have had so far focused on populations and how they are changing over time. Of course, we also looked at evolution, and where we looked at average population traits again at the level of sort of average population level, and how that was changing over time. So irrespective of we were looking at ecological dynamics or the evolutionary dynamics, we largely focused on population and how it was changing over time, and we ignored basically this multi-dimensional scale diagram, that is called it multi-dimensional scale diagram, but we were focusing on basically one slice of it. Okay, so in this course we are sort of going to go across this three-dimensional space in many different ways, and we will learn how do we understand dynamics across in this large complex space. And in the process, the focus will be, as I mentioned, space as well as stochasticity. Okay, so how do they arise and what are their implications? We will try to understand all of this. Okay, so since we have focused a whole lot of stuff on populations over large time scales, what we will do and what we will start in this course, we will begin with individuals, and we will actually look at a very short time scale. What happens in their very short time scales? We will not even go to one generation. Okay, so now that I have given you this background, let's start with understanding individuals and what they do on short time scales. So can you tell me what are the important biological processes that happen at the level of individuals on short time scales?
Foraging or
Absolutely. On short time scales, foraging is one extremely important phenomenon. Okay, and that's precisely what we will initially focus on. Okay, so sort of to what does foraging involve, by the way? Foraging at a very, very basic essence involves movement of organisms. Okay, so to understand foraging, we need to understand movement of organisms. So what I will now do is I will show you a few videos, few images of some interesting phenomenon of movement. Okay, let us see how will I do this. Share. Can you see this now? I put together a few slides to motivate this set of slides. Okay. Okay. Animal trajectories. Okay. Here, let us start with some of the very basic units of individual cells. Okay. Let me know if you can see something happening there. I don't know how well you can see this. I hope my network is reasonable. Let me play this again. Okay, were you able to see something? We see that there are lots of, it's a dark background. There are a few things that are jingling around. And what these color lines show are basically, if you were to fix one color on one cell, basically what you're seeing here is a bunch of cells that are moving in some biological context. Basically, this is actually in an experimental setting. This is not truly in a biological context. These are just cells that are kept in a dish on two sides. And when you separate them on two sides, there's an empty space in between. They fill the gap. That's precisely what's happening in an experimental setting. It's some of the context where is important. That of wound healing, for example. That's one useful context to think about, where there is a wound and cells close the gap and they they repair, right, and heal. So that could be this experimental setup could be thought of something on those lines. And what you're seeing here are these color lines are basically cells and how they are moving over time. Okay, let me give you another. So this is again the same same sort of data, but here the difference is that in the previous one I was actually showing you a real movie of them from the microscope. So what you are seeing here is basically that if you have taken out all tragedies from the movie and if you just plot the tools, this is how it actually There are three types of cell I'm showing here. I'm not providing you too many biological details here. Okay, on the leftmost, you can see that the blue point represents where they began, and the red point represents where they ended after a 15-hour gap. Okay, and the central one again shows the same thing, except that you can see the trajectory is quite different. And so is the one on the right side. The trajectory looks quite different compared to the one on the left side. Okay, so they are actually in this case three biologically different scenarios. Okay, and for example, you can think of one scenario as a healthy set of cells, the leftmost one. The other two probably are not healthy cells. And what is interesting that you're observing here is that they seem to move in a different way. Okay, so this motivation for understanding, organisms at very small time scales and how they're moving. Because by characterizing the movement properties, maybe we can say something about the biological function. Okay. Let me give you more examples. This is an example of C. elegans trajectories. Now, the moment you begin to look at organisms, bacteria, C. elegans, and so on and so forth, many of the organisms have rather interesting movement properties. If you look at very fine time scales, the way they, people have characterized different movements they have. For example, in the case of C. elegans, there are reversals. I mean, I was certainly, I think I had a video, but I forgot to put that in, where actually C. elegans that sort of moves, has a very interesting reversal phase, just literally retraces the path it took over short time scales. And then, it has, of course, phases where it just pauses, and it has phases of omegas, omega turns. You can see all in these areas here, we sort of they sort of turn back. And there's a fourth one which I don't fully know what exactly it means. I have sort of forgotten. But nevertheless, the point is that if you want to understand the entire trajectory of organisms, there are different phases of movement, and you put together, you might begin to make sense of how they move. For example, in this context, it could be a foraging context. Now, I'm going to elephants moving. This is, in this case, it's elephant moving in Kruger National Park, South Africa. So unlike C. elegans or cells, where you could have a microscope and you zoom in and record, here what you do is you put some GPS collars on animals, and then the GPS sends information on where exactly animals at some interval that represent their movement. So here, what you are seeing here are within day movement. So the stretch that you're seeing is the 24-hour movement, and I think that when each stretch has data every 30 minutes, so or maybe every 1 hour, which means there are about 12 points. Okay, so this is how they are moving over a period of time. Okay, and you can look at the same at a much longer time scales. You can also look at them on time scales of months, how they are moving across the landscape across months. Okay, of course, here various landscape factors, which are the good foraging grounds, and seasonality of the resources. All of them begin to play an important role on how animals are moving, right? So those were, we are sort of moving across scales. On these are birds. As you know, birds are really fascinating. They move a lot. This is an example of how wandering albatrosses, they move over I think it's a period of 1 day. Okay, this is the trajectory of their movement. You can see that there are some interesting features in them. So the basic and then each biological system has their own features. and that which in turn depends on the biological context they live in. Okay, so to understand these movements, uh, we can ask the following question: is there sort of, is there a mathematical framework to begin to think of these questions in ways that uh, biological observations alone cannot help you do? Okay, so that's the broad way we will think about these problems. So for example, I'm not going to solve any of the specific biological scenarios I showed you, but we will actually look at much more how can we make sense of these type of animal movements from a mathematical point of view, because often when you begin to think mathematically, you try to simplify, and that's a strength, and that provides a strength of being able to make some important quantitative predictions, and and if you apply them, maybe they provide some important insights as well, biological. Okay, so with that motivation, let me now go back to the focus on context we just came up with, which is uh, individuals who are moving on a landscape. Let us think of the context of foraging. Okay, so let's think of two scenarios. Okay, uh, again in the context of foraging, that of abundant resources and that of very sparsely distributed resources. If an animal has to now find resources, which is an easy scenario, it's sort of it's a giveaway. When the resources are abundant, there is really nothing much that one needs to uh, there's nothing much the animal is being challenged. They wherever they step, they are going to find resources, and therefore it's a sort of easy foraging problem for animals to solve. And perhaps you can say that as an extension, if you are interested in building a mathematical theory or framework, it's also probably an easy mathematical problem to think about. So maybe it's not such a difficult problem. So the harder problem really is when the resources are distributed in a really sparse way on a landscape. Okay, how should animals then, right, search or move? Okay, assuming that animals only have only local information, they do not know where the next resource is located. They cannot see. They are so sparsely distributed, their sense systems cannot detect them. So in such a case, how should animals move? Okay, so that's an interesting question to pose, and that also seems mathematically a not very obvious problem. And how do you solve? How do you? What's the solution for this problem? Is not necessarily very obvious, right? So one way to start thinking about this problem is to use the framework of random walks. Okay, because animals don't know where is the next resource. Also, the next thing, the best thing they can do is to then move randomly, because they anyway don't know, where they have to move randomly, and then maybe hope that they will hit the resource in the process. Okay, so to see if that approach really works, so what we will now do is introduce the basic framework of random walk. So this is a repetition of one semester. So this will be a small repetition. Okay. So to make life very easy mathematically, so we will start with the assumption of a one-dimensional world. I know it sounds crazy, but there are some instances where one dimension isn't a very bad assumption, even in biological context. For example, imagine a river, right? So for all practical purposes, that's true. That's basically for a fish swimming in the uh, river, it's basically a one-dimensional world, right? Um, or think of an animal that is constrained on a sea coast. Effectively, again, it's in a one-dimensional world. Okay, so it's not too bad an assumption. So it can happen in some situations. Okay, so let's denote xt as location of organism at time t. So here is how we define random walk. So the location at the next time step is defined as previous time plus, with probability of, which means you have moved, let's say, the right direction, which I'm representing by +1 unit, or I moved left in the left direction with equal probability. Okay, so in writing this, not only did we assume that the world is one-dimensional, we are also going to work in discrete space, and we are working with discrete time. Is that fine? This is the the definition of a very, very basic random walk. Okay, so before I go further and discuss how do we analyze and make some quantitative sense of this random walking behavior, let us broadly take a pause and broadly think about random variables. As I mentioned in the class and in the course instructions, some knowledge of random variables is essential for this course. So I'm just going to briefly sort of tell you what all I expect that you already know. Okay, so first and foremost, if you have, let's denote by any variable you like. Let's call this y. Okay, when we think of random variables, the most and the sort of a complete description of random variables is possible if we know a few quantities. Okay, and that would, the most basic among them will be what is called PDF, which is probability density function if y is a continuous variable, or we also call it a mass function, probability mass function, if y is discrete. Okay, now this is for discrete random variables. This is for continuous random variables. Okay. And once we know, let's denote this by f of y. So what does this tell me? So let's do a plot. So if I'm plotting f as a function of y, I'm assuming y to be a continuous random variable here. This tells me for at any given value of y, what is the density of this probability function? What does it really mean? It means the following. If we have a variable y and if we have a variable y plus dy, f of y dy will give you the probability that the random number you have picked falls in the range let's call this y0 and y0 plus dy. Okay. So that's the sort of way to understand that probability density functions, which is a bit harder to understand than the probability mass functions. For discrete cases where you only have probability mass function, f of y basically represents the probability that the event y happens. So that will be the definition for the discrete variable. Whereas if it's a continuous variable, you have to think in terms of densities and in terms of intervals. Okay, so usually this provides the complete description of the random variable y. Okay, once we know the probability density function, we can calculate a whole bunch of quantities. For example, the mean, okay, which we also sometimes denote by mu, will be basically this integral. Okay, so for example, if y takes all the way from minus infinity to infinity, this integral will tell me what is the average value of this random variable given this distribution. And we also define variance, which is basically how variable is this, how distant are the random numbers, how spread out the distribution is. Or if you were to sample a large number of random numbers, how spread out they are compared to the mean. Okay, so larger the variance, the farther the random variables will be from the mean value. Okay, so usually when we think of, in biology, when we think of random variables, we often think of mean and variance, and almost everybody's taught about mean and variance. We rarely think of the entire distribution. Okay, and that is extremely important. So understanding the entire distribution is really, really important. So therefore, always keep that in mind, that the complete description of a random variable requires us to know the entire distribution. Of course, when you have really small amount of data, you often have to be happy with just knowing the mean and the variance. Okay, but when we are doing theory, we are really not constrained by the number of data points. So we think of the entire distributions, and we think of mean and variance in addition to the entire distribution. Entire distribution is what we really like to understand. Okay, so that's about basic things about random variables. Now, another very important concept in random variables, that of independence. Let's say there are two random variables, x and y. Okay, so I have drawn these two random variables. Two independent random variables sort of intuitively basically means that when I draw the second random number, it has no sort of there's one question in the chat, and answer later. Okay. Basically, when I draw two random numbers, there is really no relationship between them. That's called independence. They do not affect each other in any way, and the way it manifests in all of our analysis is really, really important. So to give illustration, let's go back to the random walk that we defined. I said that at x t plus 1, animal moves either to one step right or to one step left, right? Now let us ask this question again. What happens at t plus 2? Okay, it had, let's say it had moved one step to right in the previous time step. Okay, does it now have a higher chance of moving to one step right, or is it independent of what happened in the previous time step? Okay, if the new decision that the animal makes is independent of the previous one, and it again moves with one, to right or left with equal probability, then the movement is independent for each time step. Okay, so and this independence is invoked very frequently. And when they are not independent, how do we know they are independent or not? We define two quantities. One is called covariance and another is called correlation. They're very closely related. Covariance between two random variables is defined in the following way. You take one random variable and subtract its mean. Okay, you take the other random variable and also subtract its mean. Okay, and then you have now basically deviations from the mean for both the random variables. Let me call this mu x, let me call this mu y, and then you take the average of this. Okay, this is called covariance. Now, if x and y are totally independent, if are independent, oh sorry, independent, then the covariance will be 0. Okay, and another matrix that's related to that is that what we use quite frequently is called correlation. So correlation between two random variables, is basically covariance between two random variables divided by the standard deviations of both of the random variables. So as you can see, whenever covariance is 0, correlation is also 0. So which one we calculate for a given instance really depends on what is more convenient and what is more useful. So by measuring these quantities, we will know whether two random variables are independent or not. Okay, that's about independence. There's another concept that comes very frequently, what we call identically distributed. So what do we mean by that? So let's take some random variable x, another random variable y. If they both have same probability distribution function, including the same parameter values, we call them identically distributed. Okay, so again, let us go back to the same very simple example that we constructed in terms of random walk. So the assumption we made was that it's one step either to the left or right? And that, so you can think of them as, I'm adding a random number to the current location. And the random numbers I'm adding are +1 or -1, right? It can take only two values. And the same two values with same probabilities also happen in the next instant of time, right? So therefore, it's identically distributed. Okay, so that means they have the same PDF. And if we include the independence and the distribution together, you often see this usage called IIDs, which means that independent and identically distributed. Okay. Okay. So this is what you will see these IIDs quite frequently. So what happened? Okay. So any questions to this point? I know it's a very brief and probably not elaborate description of the random variables that I expect you to know, but I expect that as you sort of keep practicing, you will get thinking about this. So remember the 3 facts we need to know. Whenever you have a random variable, you think of mean, that you already know. You think of variance, you already know. Think about dependencies, in terms of correlations and covariances. And finally, think about the entire density function, probability distribution or density function. Okay. So, as long as you sort of think of this in a simple sequential way, mean, variance, correlations, and then the entire distribution. Remember that every time the random variable comes, ask these 4 questions. What are these quantities going to be? It will provide you a way to think about random variables. Okay. So any quick questions before I move forward? There was a question here, can't animals be at rest? Do they always have to move? Absolutely, you're right. Where, if you are trying to apply this to real organisms, they also have a rest phase. And in fact, the C. elegans examples I showed had a pause phase. You should be able to easily modify this model to account for that rest phase as well. So for example, you can say that animal moves to plus or minus 1 units at some probability P, but it also can stay at rest with some probability, which is 1 minus 2P, right? So that will give you a model of random walk, but also allowing for rest. Any other questions?
So I can ask question by audio, right?
Absolutely, yes.
Okay, great. Okay, so can this random walk be augmented with something like memory, where the animal?
That's a very good question. Yes. So again, what does memory mean in terms of the properties of random variables I have described?
So it is so it is not independent. The 2 time points.
Exactly, right? Yeah, exactly. Yeah. So absolutely, that's correct. It can be done. Yeah.
Okay.
We will do that. We will do it on future random walk models. Okay. Any other questions?
Yeah, I have it.
Yeah.
I am a little confused about how variables can be both independent and identically distributed.
How are they different? Is it, does one guarantee the other? Is that your question?
Yeah, I mean, if they're identically distributed, won't they be correlated?
Oh, okay. That's a good question. So let me ask you a simple question. Let's say I do a coin toss. Okay. I will get head or tail, right? Is it fine? So coin toss has 2 possible outcomes, head and tail, with some probability P and Q, let's say. Okay. And you toss the coin. Okay. That's unless let's call the random number Y now. That can also have 2 outcomes, head or tail. Will they have different probabilities?
They should.
Unless we have a very weird way of tossing, assuming we toss same way. So if my if my coin tosses outcomes are called random number X, whose outcomes are head and tail, right? With probability P and Q. And yours are called Y, whose outcomes are also head and tail, with probability P prime and Q prime, right? Now, isn't it, assuming we now toss in identical ways, P prime will be equal to P and Q prime is equal to Q, right? Now they will then become identically distributed random variables, right? Is it fine?
Yeah, I think I get it. Thanks.
Okay. Yeah. Any other questions? So think about this, independence and identical. You can wonder, if two are identically distributed, ask, does it necessarily mean independence? Likewise, ask the following question: does independence mean that do they have to be identically distributed? Can do one mean each other? The answer is they're actually independent concepts. Okay, so one doesn't guarantee the other. But think about it, it's not very obvious. Sometimes you might get confused. Any other question before I go forward?
Yeah. When with the random walk that you have described, if the organism has an equal probability of going in either direction,
yeah,
doesn't given enough time, won't the net displacement just be zero?
That's a good question. So that's what we will start computing in the next. That's what we'll just start computing now. So as I mentioned, so I have now described basic properties of random variable, right? Is xt a random variable now? Is that right? So by the way, in my definition so far, I haven't told something very crucial. Okay, let's assume that x of 0 was 0 without loss of generality. Okay, so the animal begins at origin. Okay, and then it follows this rule at every time step t now. Okay, so the question that somebody just asked was that, will the net displacement be 0? Let's just find it out. Okay, so we will now calculate properties of random walk. Remember that xt, which is the location of animal at time t, is a random variable, right? Do you agree with that? Okay, and let us now also write in a slightly more general way. I told you that this is plus or minus 1, but it could also be any plus or minus. It could be a more general quantity. Okay, xt could be xt minus 1, right? Plus or minus a, where a is the step length. Okay, with equal probability. P is equal to half, or plus a or minus. Is that fine? Okay, this is a random variable that we have defined. Remember that there are two random variables in this expression and the way we have defined random walk. The fact that the animal is deciding, so a is a fixed number, right? We have fixed a. We will not change a, but the fact that it could go to plus a from the current location or minus a from the current location. That's where the plus or minus is the randomness part of it. The direction that the animal moves, that's the random part, not a. And because now I'm adding that to x, current location, the resulting allocation also therefore becomes a random variable. Is that clear to everyone now? Okay. So with that, now just remember, so one question we will be interested when things move. We know from physics, high school physics, that we would like to understand displacement when things move. What is displacement at time t? Let's denote the displacement by d. Sorry, my handwriting is not the best handwriting in the world. Okay, x of t minus x of 0. Is it correct? Okay, so that's the displacement from the origin. Okay, so now what is the average displacement? Let's call that this. That would be x of t minus x of 0. So is everyone familiar with the angular bracket notations? Is everyone comfortable with the angular bracket notation? Okay, so in case there's somebody who doesn't know, who is very shy to ask, okay, if there is some random variable x, angular bracket of x means the average of x. That is basically this integral I defined. For a continuous random variable, that's the integral. If it's a discrete random variable, it's basically summation of all the values that x can take multiplied by corresponding probabilities. Okay, so this angular bracket basically means average. Yeah, sure.
Yeah, so the angle bracket, is it like a sample average, or it could also be an expectation theoretically?
So I'm just defining it as, for that random variable, you find the PDF and then you average over the PDF.
Okay.
That's an expectation value. Okay. And there are, what's the difference between an ensemble average and this average expectation value? Why do you think they will be different? They don't for most cases that we will consider, they will not be different. So we don't even have to worry. We can use them interchangeably.
Okay.
Yeah. Again, when you have independence and identity distributed, you can just use them interchangeably to a large extent. I don't know, there might be some mathematical theorem that say you cannot under these circumstances, but for our purposes, you can. Okay, so this is the angular bracket notation. Angular bracket basically means the expectation value or just the average value. Okay, so this is the average displacement. Okay, and that is equal to average of xt minus average of x0. As I already told you, we assume that the initial location was 0. So therefore, this basically is 0. So displacement, average displacement is nothing but the average location at time t. So what is that going to be, right? So for that, we have to go back to this equation. Calculate this quantity, okay. The average of average displacement. Oh, sorry. So let us use this equation. So xt, as we know, relates to xt minus 1, right? Okay, xt minus 1 plus or minus a. Okay, so now, so this is a very awkward notation. I won't do this. Okay. Okay, so what's really happening here is, there are two values that xt can take, right? Okay, in fact, there are just two discrete values xt can take. What are those? Xt minus 1 plus a, right? Right? That's one value it can take. What is the probability of occurrence of this value? It's just half of this. Is it fine? And then with half probability, it can take another value, which is xt minus 1 minus a. Is that right? So any questions on this? How I arrived at this expression for xt average? So whenever we have this expectation value or these angular brackets, what does it mean? We want to know the average of that variable, right? So now remember, now xt can take discrete values, right? It's the previous location plus a or previous location minus a. Okay, there are only two values it can take, and you multiply both of the values by corresponding probabilities, and therefore you now have the average. Is that fine with everyone? Okay, now as you can see, if you now agree with me on this one, you see that these two will just cancel out, and half of xt minus 1 plus half of xt plus 1 becomes what? Just xt minus 1. Is that fine by everyone? So average of xt is basically nothing but xt minus 1 itself. Any questions on this?
Yeah, one small question.
Yeah.
While taking the average of xt, why are you taking the value of xt minus 1 and not the average of xt minus 1? Because I'm assuming it's a process,
Because,
right?
okay, that's a good question. That's a good question. So I am starting with a given value of, for a given value of xt minus 1. What's the value of average value of xt is what I have just computed. Is that fine?
Right. Okay.
For a given value of xt minus 1. Okay. Now, right. Of course, now you can also now the same question. Now the xt minus 1 itself is a random variable, but I really want the final average, right? So what does that require us to do? Okay, that requires us that we calculate the average again, right? Because this assumed a conditional value, a given value of xt minus 1. Therefore, this is not satisfactory. We have to just apply this recursively. What is the average value of xt minus 1 now, right? If I now ask the same question, what will that be? For a given value of xt minus 2, it will be, if I were to apply the exact same calculations, I will get this, right? And then we can keep on doing this recursively. What do we then find? 0. Any questions on this? While the average value of xt itself is xt minus 1, the average of xt minus 1 itself will be xt minus 2. And you can just keep on applying all the way to x1. And what you will find is that the average of x1 is 0. And if I now look at the average of dt, that will be basically nothing but x0. And since we said we started the origin, the average value of dt across all possible paths will be nothing but 0. Is it fine? Any questions? So indeed, whoever asked this question is right. You know, the average displacement for the random walk is basically 0.
But
now,
what if you don't start at the origin? Then you'll get some non-zero value, right? So does that
hold on for a second. No. Hold on. Okay. Remember what happened here? We had xt minus x0, right? If this was non-zero value, this would still be around. Do you agree with that?
Right.
I wouldn't
No,
have cut this to 0. Yeah. So what you get is xt, yeah, you know the answer, right? So because the average of xt is x0, they just get now cancelled.
I had a small question.
Sure.
When we're doing this for like a real world system, what A and B also typically differ? So for example, if you took the river as a 1D example, a fish might be more likely to swim downstream than upstream and also travel more downstream than upstream. Given like, say,
that's a great question. So what you're saying is that xt is equal to, let's say, xt minus 1 plus a. That's one possibility, right? Another one is this, right? You're saying that this happens with probability p, and let's say this is with probability q, right? You're saying that maybe p is greater than q because plus a is downstream. Is that what you're saying?
I'm also saying it's possible for the A's to differ because a fish might get carried by the current.
Very good question. Yeah, that's the first point. By the way, this is called what we call biased random walk. Okay, the next question. So I will have an assignment. Assignment 1 has a question on this. Okay, and the other question that you asked, which again is a very good question, is that xt is equal to xt minus 1 plus a, where a itself is a random number, right? Is that what you're saying?
Yeah, pretty much.
Random number, not a constant. Absolutely possible. You will have another assignment question on this. Okay. Okay. For example, you can so now you can also think about the following, right? if the average value of this random number is 0, right, then we go back to the previous case of unbiased random walk, right? But if it is, let's say, non-zero, it becomes biased random walk. So whatever we have been doing so far, is a unbiased random walk. That's the scenario for which we are calculating mean displacement so far. Okay, so what I will ask you to do in the assignment is, if you do have a scenario like this, how will the results change? Okay, that will be the assignment question. Is it reasonable? You must be able to do, right? Just have to go back, replicate all the steps, but under the assumption that now A is a general random number. Okay, excellent. Okay, so now let's go back. So we have now looked at the fact that the mean displacement is 0. But do you remember the trajectories I had shown? Trajectories I had shown in the in that cell migration scenario, right? Okay. Or maybe what I will do the following. Okay, I have now defined so far one-dimensional random walk with no bias, right? What I will do is, it's actually fairly straightforward to generalize 2 dimensions as well. What I have done for you already, and in fact, there is already a code that I've uploaded on Canvas. Let me share a different window now. Can you see the screen now?
Yes, it's visible.
Okay, excellent. Okay, so this is an R code where I had requested all of you to install R and R Studio on your computers. So what I have done here is basically a simple R code. Can you see this? By the way, should I increase the font size or is it okay? Line number 1, I'm just doing line number. It's a simple R code to simulate a 2-dimensional random walk. Okay, I just wrote this last night and I have also uploaded it online. Okay, so now this code has 2 options. An option called animate. If you choose 1, it actually will animate. It will be very slow to run. It animates a random walk in 2 dimensions. If you choose 0, it doesn't animate. It will just directly show the trajectory at the end of 1000 time steps. Okay. Let me just do 0, which means you will not see the animation. You will just see the final outcome. So if everything works well, if I click this source button, it runs the entire code. Are you able to see this now? Are you able to see this trajectory?
Yep, it's visible.
Okay, excellent. So blue was the starting point and the red one was the end point of this random walk. So I will not go through the code. I have written, I think, sufficient number of comments. That way you should be able to do this on your own. Okay. So in fact, I have actually done 2 changes in this code, by the way, compared to what I have just described. This is a 2-dimensional random walk, not a 1-dimensional random walk. The first change I have made. The second change is that every step is not of fixed length. So for example, look at these 2 lines here. So at every time step, it chooses a rand x, how much distance to move in the x direction. Rand y is how much distance to move in the y direction. For each of them, it picks a random number which is uniformly distributed between -1 and +1. Okay. So the random number I pick will be a continuous random number between -1 and +1. Whereas the model I described to you just now is actually +1 or -1. Literally, there are only 2 possible values, right? I have made these 2 changes. This is how it looks like. So the blue is the origin where it began. Okay. And after 1000 steps, it has come to red. Okay. Let's just run this again for fun. Is that fine? Now, blue is the starting point. It has ended up somewhere here now. somewhere near minus 12 and minus 5. Now, blue is the origin. It has now ended up at plus 1.5, but minus 10 close. Okay, minus 10. Okay, let's run again. Okay, origin is here. It has now traversed to a positive quadrant around 30 and 10. Okay, so as you can see, if I keep running, I'll get different realizations. We call them different realization. Each run is called a different realization. Okay, you can see it's all. Sometimes the final, the final point is in the. If we were to think of 4 quadrants in the, in the 2-dimensional space, you can see that depending on the run, depending on the realization, they can all be in different places, right? The red is the final point, by the way. Is that fine? So what's really happening when we say mean displacement is that if I take average of all of this, it actually will be 0. Average, if I were, so I have this displacement vector, right, from blue to red. If I take average of all these blue to red displacements across many realizations, then that will be 0. Is it clear to all of you?
Yes, sir.
Okay. But you do see that, does it mean they haven't moved? See, but you see that there's something about the average that is unable to capture what's happening. What is that?
Like the spread, like how far it's gone.
Right. So although the average displacement is 0, if you were to look of spread from the where you began, origin, to where it ended up, right? If you look of that spread, that is non-zero every time, right? It has actually moved away from origin, except it moves in different direction every time. So if you were more interested in spread rather than just the average, that average is clearly not capturing it, right? So the displacement, because it has that vector, it's a vector and it has a directionality and a sign. The average of it actually, it cancels out all the spread. Okay. By the way, I want to show you one more, this one, and how does it look when animated? Okay, actually it's really fun to watch. Let me know what you think, if you agree with me. So the red one is that you can think of as where the animal is, 0, blue is where it began. This is how it's moving. Can you see it as an animation?
Yes.
Okay. It almost looks like an animal, right? Bacteria moving. Okay. So you can, I have uploaded this code, so you should be able to play around with this. But what these simulations and the the plots I showed you indicate is that the average displacement is too simplistic a measure, and it's unable to capture, as somebody rightly said, the spread. Okay. So let's now calculate the spread. How do we calculate spread of a random variable?
We can look at the variance.
Absolutely, right? Absolutely. Okay, so I know, again, remember the 4 sort of, points I mentioned. Whenever you have a random variable, think of average or the mean value, think of variance, covariance or correlation, and then the final distribution itself. Once you have all these 4 quantities measured up, pretty decent amount of stuff about this random variable. Okay, so let's now look at not just mean displacement, but let's look at the mean. This is called mean square displacement. The short form for this is MSD. So what is MSD? MSD at time t is basically, you look at the location at time t, subtract the initial, this is the displacement, right? So this is the displacement, you square the displacement, and then you take the mean value. Okay, is that fine now? So what we were earlier doing was, we didn't have the square, we were just doing the mean displacement. Now we are squaring the displacement and then we're taking the mean. So this is what it becomes. So let's see what happens to this. We have average of xt square minus 2x0 xt minus plus x0 square. Is that fine? So now again, I'm going to assume that basic probability theory. When you have average of many terms which are added up, it is same as addition of the each term taken as an average. Okay. Is that fine? So average of this set of summation is summation of the averages. Okay, so let's simplify this a bit further. Okay, now again, 2 is a constant. So again, I'm going to use another probability theory calculations you must know. When you have average of a constant and a random variable, the constant can be taken out as a product, right? So 2 is a constant. X0 is also a constant because that's initially given, right? So I can take 2x0 as a common factor, and we have this. Is that fine, everyone? Okay, now look at this. What is the average of xt? We did this computation last time in the previous slide. Average of xt is basically x0, right? Because average of xt is xt minus 1, average of xt minus 1 is xt2. If you successfully apply average, you will get that xt average is same as x0. Okay, so this is nothing but x0. And what is x0 is a constant anyway, and average of a constant is basically the constant itself. So this is basically x0 square. So xt square minus 2x0 square plus x0 square. This is nothing but xt square minus x0 square. Is everyone with me so far in terms of algebra? Any questions? We have one more step to do. We would like to know how does this depend on time. So we know the average of xt, that is just x0, right? That's what we did in the previous page. What is xt square? That's what we should do next. But before I do, I want to know if you have any questions. No questions? Okay, great. Okay, so now we need to find the average of this. Okay, now remember again. Okay, xt was xt minus a with probability half, right? And it was xt plus a with probability half. Okay, so let's just do xt square. So xt square will be this square with probability half, right? And this square with probability half. Okay, so xt square minus 2axt plus a square with probability half, xt square plus 2axt plus a square probability half. Is that right? Oh, sorry, this is xt minus 1. Sorry for really bad handwriting. Very cluttered writing. Any questions? So what is xt square now, average? So whenever, again, remember the basic principle of any average. You should know all possible values it can take and the probability of each of those, right? So it can take two values, this or this, and they both occur with same probability. So it's basically this plus this into half plus this into half. As you can see, this minus term just cancels out, and the other two terms are identical. So basically, without doing long algebra, I hope you are convinced that this is just this. Is that correct? So xt square average is xt minus 1 previous location square plus a square, where a is the constant step length. Okay. Now what do we do? What's the next step? No, just like in the previous mean calculation, we just find the recursive rule now. So likewise, if I were to apply this the same rule, same sort of algebra for xt minus 1, what do I get? Xt minus 1 square will be xt minus 2 square plus a square. Is that right? Oh, there's no average here, sorry. Is that right? And then I can apply this to again xt minus 2, and I can apply this all the way to x1. Is that right? So now, replace this. Take the average of this first blue box here, and then you can replace the average of the right hand side here with this equation, and then you keep on doing this. What will you get? X0 square plus t times a square. Please let me know if you have a problem with this. Is it fine? Okay, now, so let's go back to the definition of mean square displacement. MSD is xt square minus x square. Okay, so MSD Hello, are you able to hear me by the way? I hope I haven't lost my connection.
Yes, yeah.
Hello?
Yeah, we can.
Yeah.
Yeah. So mean square displacement is t times a square, where a is the step length, and it is proportional to the number of steps you have taken. So t is the number of steps I have taken, right? So mean square displacement is proportional to t. Okay. So this is a very, very fundamental result of random walk. Okay. A fundamental property of biased random walk. Any questions to me so far?
So how do we interpret this? Since this is square of distance, do we say some root t times a corresponds to some distance spread in this case?
Absolutely, yes. Yeah. If you were to think of distance spread, distance spread is proportional to root t. So now just think of, to understand this a bit better, think about the following, right? So left hand side is the square of the distance, right? Okay, now if you had a ballast, what we call directed motion, what do you expect if you had a directed motion? If an organism was moving in a directed motion. What do you expect for MSD as a function of time? Let's assume it is taking constant step length A at every time, but only in one direction. Extreme case. What do you expect this to be?
T square.
It will be T square A square, right? So you expect that the spread will be proportional to T square, but what do you have it here? You only have a T. Okay, and that's because there is a lot of, the spread is reduced because of the randomness of the movement. You also come back frequently and cancel out where you have moved, right? So that's why the spread is less when there is a random walk. Okay. And this is actually a very nice and measured in principle, right? At least if you can measure mean square, if somebody gave you a trajectory, right? You can compute MSD from a trajectory as a function of T. You can actually make a hypothesis. I don't, oh, did I write MDS? Sorry. Okay, you can assume that, real world is complex, therefore, this actually has a behavior alpha, T power alpha. One is when random walk movement hypothesis is correct. Two is when an organism moves in a directed fashion. Maybe the real world is somewhere in between. We don't know, right? So you can say MSD is T power alpha. So you can actually then, plot logarithm of this with logarithm of T, right? What do you expect in such a case if this is true? So logarithm of MSD, right, will be alpha times logarithm of T, right? If it is true, right? So therefore, you will get some relationship. The slope of this line is equal to alpha. And what do you need to compute MSD, mean square displacement? You just need the locations of the organism as a function of time, right? With that, you can actually calculate mean square displacement. And if with the plot of log of MSD versus log T, you can estimate the slope. And therefore, you can actually estimate where does the real organism fall? Does it fall in the extreme of, Brown, a random walk, which is, which has a mean square displacement exponent of 1, or is it a directed motion? Is it T square? For example, migratory birds are cells trying to move towards clearing up a wound, right? And they will all be directed motion. There you can expect values of alpha close to 2. Whereas if it's moving randomly, you will expect values of, value alpha values close to 1. Okay. So this is alpha 1 is random walk. It's also called Brownian motion. Also called diffusion, diffusive motion. Alpha 2 is ballistic, persistent, you can say, directed or persistent. And when you have alpha between 2 and 1, we call them super diffusion because it's moving much faster than diffusion. If alpha is less than 1, also called subdiffusion. And both of these put together, they're called anomalous diffusion. Of course, why exactly diffusion? We will come to that in a couple of classes later. Okay, so if you have no more questions, I will stop and I will give you a group assignment now. Is that fine?
So I have a quick question.
Yeah.
So these deviations from alpha cannot be directly, we can't point that difference to whether the A is random or whether we have different P or Q, right?
That's a very, very good point. So let's, so part of your assignment will be today, which I'm going to give you now. Okay.
Sir, I had a question.
So, yeah, sure.
Can we sort of reverse engineer the, like, as I understand, a biased random walk would have something in between 1 and 2 for the alpha parameter?
That's a good question. That will be in the assignment. What will be the alpha for biased random walk will be a question in the assignment.
Okay, so like my question was slightly building on that, but if we have a given alpha, can we estimate the P and Q?
Can you estimate what, sorry?
Can you estimate the probabilities of moving left and right, assuming it's like a 1D system?
Hey, so if we had data, can you estimate P and Q? So if it was whether it's a bias? Yeah. That's a good question. You should think about it. How will you do? Okay. So so this is the what we call lab or group assignment for today. So I have shown you all the results of mean square displacement under the assumption that xt is equal to xt minus 1 plus or minus a with equal probability, right? So far, this is what we have done, right? With this, we showed that MSD is t times a square. Okay, but let us consider a slightly more complex case where we assume that xt is previous location plus a value a step length, where a is do you have a favorite distribution in your mind? Is not a constant. Okay, what could it depend on? Let's assume a normal distribution, okay, with mean 0 and a variance sigma square. Okay, find MSD. That's the assignment for today, that we will work in groups. Is that question clear to everyone?
So this is plus or minus a, or is it purely directed only plus a?
What do you think? So here is the so look at this. A is a normal distribution with mean 0 and variance sigma square. Right? What's the normal distribution?
Right now,
right now, a normal distribution has this, right? 1 over square root of 2 pi sigma square e power minus x square by 2 sigma square. So x can take values from, okay. Any other questions? I hope I wrote this distribution correctly. 2 pi sigma square normalization. Okay. Any other questions? So shall I stop sharing the screen now? You have noted down the question. Okay, I'll stop now. So we will work in groups. Let me see how the. So if you have no further questions, I will start the breakout room. Some of you are not yet assigned to any group. For today, you may be assigned to some random group, and I request the other group members where somebody may randomly pop in to cooperate. So I will so unassigned members, I will assign them to those with 3 members.